The recording. Okay.
Okay, so let's start. So Juan, thank you for presenting today, and thank you to everyone who's coming attending the talk. So today, Juan is gonna present his it's not your latest work, right?
Yeah.
But you started again the project now because it's super interesting. But it's about feasible learning, sample-centric machine learning. So thank you again for presenting today, and the floor is yours.
Thank you, Damien. And thanks everyone for being here. I hope the iClear rebuttal is going well, that you're getting some sleep. As Damien said, I'm going to talk about feasible learning. You may have seen a poster outside of the restrooms in 6666. Right in front of it, that's this project. The location was chosen at random. So feasible learning is it's actually a paper we submitted and presented at ASTATS 2025 with a bunch of collaborators from Mila and from the University of Pennsylvania. Let me actually, 1 second, I'm gonna get my laser pointer. Okay, good. So we presented it at ASTATS 2025. This is one of those funny papers where there's 4 co-first authors and then 2 co-supervisors. More on that later. If you want to have the paper at hand during the presentation, or if you want to have the slides at hand, these QR codes can get you there. In case you want to navigate at a different pace, you want to go back to something I perhaps went fast through. So, I'm going to talk about feasible learning, which is a way to do learning that is different from empirical risk minimization. So first, let's discuss a bit empirical risk minimization and why we might be able to improve it. So you're all intimately familiar with this sort of setup where what you're doing is you have a data set, a training set, you compute the loss for every sample in that training set, then you compute the average across the different points, and you minimize the average. So this empirical risk minimization framework is theoretically justified. So we know that with high probability, if you minimize this empirical average, you will be optimizing the true test average on unseen data. And we also know, part of the success of ERM, the reason it has gotten us this far in machine learning is also its ability to scale. It is very fast, especially if you do first order, or to a certain extent also second order optimization to minimize this. And it has an incredible ability to generalize that even seems unlikely from the theory. Like it goes more than what we get from the theory at times. But there is some room for improvement, and I want to focus on 2 aspects of ERM that could use some improvement. The first one is that it optimizes the average. So there is a notion of fairness that is lost to ERM because like looking to get the best possible average, you might end up sacrificing some examples. If you're familiar with any of the fairness literature, it's common for underrepresented groups to have worse performance than, let's say, a majority group of the data when you train through ERM. And another aspect is that ERM doesn't know when to stop. What I mean by that is that it's really pushing to get the minimum loss even beyond what's really useful or necessary. Even if you're already classifying all of the points in your data set correctly, ERM will keep on pushing, and that's when you get exploding logits, overconfidence, and this sort of behavior. I think those, I think those 2 ideas are fairly intuitive, but just to hammer the point home, here are a few plots arguing for this. So here we have different plots where these come from a series of users who are using a language autocomplete system. And what you're seeing is the satisfaction, retention, and user count throughout the time that people were using this system. I want you to focus on the green curve. there's two green curves. There's one dotted one over here on the top. There's one not dotted, like continuous one on the bottom. Those are when people were using models trained with ERM. Now the dotted one is like the majority group. That's what the model was mostly seeing, what was dominating the average. And the straight curve is a minority group. So what's happening here is as people keep on using a system that was trained with ERM, people from the majority group who are represented in the data are more satisfied with the system, and so they continue using it. Over time, people from the underrepresented group stop using the system, and there's also a notion of performativity here. Over time, if few people from a group are using the system, then fewer data from them is being fed, and this creates a feedback loop. So the point is, ERM, we could have a more sample-centric way of learning that is more concerned with the individual experience of every user, and that has potential benefit for companies. There's also the other aspect about optimizing too much. And so we all know ERM can overfit. If you have enough capacity, ERM can even fit random labels, which is not great. And this can also fit towards the idea of it optimizes too much, which can hurt calibration. It can hurt. It can make models too confident. You all know how models can be wrong and be too confident even though they are wrong. Here we have a few plots of measuring calibration. So it's essentially how confident the model was in the prediction, and then how accurate it was within that group of predictions for that certain confidence level. And as training progresses, the model is super confident, and eventually it only, you kind of get exploding logits. It's kind of the idea here. And that's also something that becomes worse through the use of surrogate losses. What I'm thinking here is there's a slight disconnect between accuracy and cross entropy. If we were optimizing for accuracy, we would stop, let's say, when you're classifying everything correctly. But if you're optimizing for cross entropy, you essentially never stop. So now I'm gonna. Were you thinking about asking something, Ren? Okay, no worries. Feel free to ask any questions. Feel free to interrupt. Happy to go on short discussions. So now I'm gonna talk about how we address, like, the step we're taking to try to address some of these problems through feasible learning. Kind of the idea for the rest of the talk is I'm gonna present feasible learning. The idea is we're gonna ask for the loss on every training example to be bounded, as opposed to optimizing for the average. I'm gonna tell you how we solve these sort of problems. We're gonna go for a primal-dual approach. So that's formulating the Lagrangian of the problem and finding a saddle point. I'm going to explain this in detail, but the point is that this is similar to doing SGD on ERM in the sense that it scales. Another aspect is I'll then talk about something we call resilient feasible learning, which is if you're asking for a constraint on the loss of every example, well, that can be a bit sensitive to outliers. Say you have some points that say you have duplicate points with different labels. Well, there's no way you can classify both of them correctly. So how do we address for this? That's going to be resilient feasible learning, which is essentially you add slack variables to the constraint optimization problem. We're going to show some experiments and relate them back to the motivation on like how this framework might help improve over ERM. And I have lots of future work, which I hope if I get you a bit excited on feasible learning throughout the talk, then hopefully we can discuss there. Yes.
You said lower bound and velocity, upper bound.
Upper bound of the loss, yes. Thanks, of course. So this is the feasible learning problem. What this is saying is let's try to find any model whose loss is sufficiently small for all training examples. And that sufficiently small is encoded by this hyperparameter we call epsilon. I'm going to give you an example in just 1 second, but You could think of this as the loss being the cross-entropy loss, in which case this constraint is essentially saying you have to assign this amount of probability to the correct class. Or it could be the squared error, any choice of loss. And just to have a quick example, so here I'm going to write the problem in a vector form, where G is just the stacked version of the losses for each example. You could think of the goal is to correctly classify some data, and you want to have a little bit of a small margin. So that means you want to assign at least 60% probability on the correct class, the 10% being the small margin. And you can do this by setting the loss to be the cross-entropy loss, and then setting this bound. Now, you can already see that depending on the choice of epsilon, this is going to be like one of the most important parts of the formulation. Depending on the choice of epsilon, you encourage different behaviors of your model. So here in the example, I intentionally chose to ask for 60% probability as opposed to 100% probability. That is connected to the fact that, to the comments I was making about ERM optimizing too much and being too confident on its predictions. Well, why did we just ask for 60%? And I'm going to elaborate a bit on what the set of solutions to this problem looks like as we change epsilon. So here's a line of the different values of epsilon. Yes, Danilo?
Why are you minimizing theta on 0 and not like minimizing G theta on 0 and then adding this thing as well?
So
not minimizing, just minimizing G theta along with the constraint as well. I don't get why you need min 0.
So, but G theta is a vector. So there needs to be a notion of which scalar would you minimize.
Then do ERM. Like minimize the ERM on theta and then add G theta.
If you do that, you're still, so let's suppose you can interpolate the data, you can get zero training loss on every training example. You would get that solution. And that means you're trying to overfit, it goes a bit against the motivation. But there's definitely, so the reason we set 0 is we want to be flexible. There's also a notion of curiosity. Since we're not favoring different solutions that satisfy the constraints, which one do we get to? But you could do different things. You could minimize the norm of the model. You could minimize some scalar metric of G, the average, the max value. It's still, I'd be curious to try other things. That's what I'm trying to say. So, okay, so what happens when we change epsilon? So here there's a line for different epsilon values. There's going to be a couple of phase transitions in the graph. If we start from the left, and by the way, as we go right, we are increasing the set of solutions for feasible learning. Since we have an inequality constraint, we want anything where the loss is more or equal to epsilon, then anything to the left of the chosen epsilon is still a valid solution to the problem. So at the very left, we have epsilon equals 0, which is saying, please interpolate the data. If you're under a scenario where you can do this, you have enough capacity to get zero training loss on every sample, then here you're telling it feasible learning to get you the same solutions as ERM. Those with zero training loss on everything. But sometimes you don't have infinite capacity, and there's a trade-off. You cannot get zero loss on every sample. So that's where we get to this next regime, which is up until this point. So here, what this is computing is the smallest. So you find a model that gets you the smallest maximum loss, where I is the different examples. So if you set this to be the upper bound, if you set anything smaller, then this problem is going to be infeasible. By definition of epsilon, you cannot make all losses, you cannot make the maximum loss smaller than this. So this is a regime where feasible learning is unfeasible, then everything to the right is feasible. So to the left, we don't have solutions. To the right, we do. And then if we stick to the example of classification, we could think of an epsilon here that asks for at least you classify the points correctly. To the left of that, we have, so to the right, we have what I call a useless regime, which is you're not even asking to classify the points correctly. So yeah, it's a bit of a, what are you trying to do? And as you go to infinity, you could even end up with a vacuous constraint where every model is acceptable to the problem. So this is useless. Then to the left of that, we have a regime where you want correct classification and you want a bit of a margin depending on how much to the left you are. You want some confidence on that classification. And you know, I suppose the correct, like the optimal epsilon, if there's such a thing, is somewhere in the middle. You don't want to be too far to the left because you're encouraging overfitting. You're telling the model to be very, very confident in its predictions. You don't want to be too much to the right because you're not asking for enough of a margin, and that can have bad consequences when it comes to generalization. You could end up just with any model that classifies the points correctly, even if it's too skewed towards some of the data. And there was this point that I was making earlier about what if you can interpolate the data. So in that case, you can choose any epsilon greater than or equal to 0, and still your problem is going to have solutions. And if you choose exactly 0, then you match the solution set of ERM. So now let me mention, yeah.
Or general question. So yeah, you motivate this by like minority groups. You have the threshold like three or above, so you have to class everything rated correctly. One thing I'm not sure about is what if you have like one sample or some group? Why would it or would it not make sense to force like correct classification of one sample?
You're thinking like an outlier?
Well, I mean, according to the teacher, it's an outlier, but maybe it depends on the problem, but maybe I'm just, or like, I don't have enough statistical like power for that group, right? Like I have one sample. But why is it good why is it good or bad if I force the model to actually classify that one like data point for, like I've only seen one signal targeted for that data point.
Right, it depends completely on the application. But in terms of the methods, we are gonna arrive at a relaxed problem in a couple of slides where you can accept not to classify a few points correctly. And you can relax the constraints for some of the samples.
I would assume that the right epsilon still needs to be fixed with like some validation set. So this might, like the generalization for that minority group might not be the one that actually forces it to be correct on the training. Because it might overfit. This is not enough data.
Right. Yes. It also, so there's a big question of what are you trying to achieve here? If you're using feasible learning to, let's say, try to compete with DRM. So I'm saying this because that informs the metric you would use when you go to that validation evaluation. Is it the average loss? Is it the loss on a specific group? Is it the maximum loss? It's a bit unclear. Depends on the application. Okay, so let me mention why feasible learning kind of makes sense for fairness. I mean, I think it's fairly evident from the formulation, but feasible learning is saying find any model that's good enough. It's not explicitly asking for anything on the average. Whereas ERM is optimizing for the average, so it can have some samples with very, very high losses, just because that allows it to fit very, very well a couple of examples, and that overall minimizes the average. So it's a bit of a more sample-centric and fair approach to learning. And there's also the component that feasible learning is happy not to overfit. So there is, if we set a non-zero epsilon, you can get solutions from feasible learning, both that have a big epsilon, but also like with a loss of zero. Like anything smaller than this works. In particular, interpolating the data works. So that's why I'm not saying feasible learning does not overfit. That's not true. It doesn't ask to overfit. There's a question of what do you recover, and that's going to be important in a bit when we talk about how we actually solve these problems. But it doesn't need to overfit the data. That's the point. Whereas ERM does push for that. So again, if you push to minimize the loss, even after you satisfy the constraints, that's not something feasible learning does. There's no need to overfit the noise of the data, for example. And one quick slide before I go to the way we actually solve these problems, and is that you might have noticed this looks a lot like SVMs, hard margin SVMs. So here we have feasible learning on the left, SVMs on the right, and the formulations are very similar. The differences are going to start to pop up in the way we solve them. So on the left, we're kind of concerned with neural networks, nonlinear models, whereas on the right, you have a linear model. You have nonlinearities, but those are usually hyperparameters in the way of like kernels for the SVM. For this paper, we went with minimize zero for FL, as we were discussing earlier, whereas the SVMs minimize the norm of the model, which gets you to the maximum norm solution. And there's going to be a big difference in the way we actually solve these problems. So let me now talk about the way we solve feasible learning problems, which is through primal-dual formulations. So there are many ways to solve constraint optimization problems. But this feasible learning problem is tricky for a few reasons. So the first three, which are, they're a consequence of we wanted to tackle feasible learning problems in deep learning. The first is non-convexity. So you do not have a closed form solution for your feasible set. You cannot compute projections efficiently or feasible directions. So, your favorite constraint optimization algorithm probably goes out the window. It's also very large scale, so we need something that can scale to billions of parameters. And there's data dependence, which makes it tricky to assess feasibility. Just because you get a batch of data points and you're feasible on them, it doesn't mean you're going to be feasible on the next batch of data. And there's, one thing that's even more tricky in feasible learning, and it's that you don't have an objective. So, think about your favorite constraint optimization method. It probably uses the objective in some important way. Projected gradient descent, where you're descending on something and then projecting, or like stuff like this. Like not having an objective is a bit unusual. So we're gonna use the Lagrangian formulation essentially. And just because I have a bit of time, let me indulge for a second on how this project came to be. Because I gave you the motivation of the fairness and let's not overfit and all of these fancy words. But the project came to be a bit differently. So it's just 2 slides. It's like this. So there's this group on the left who will do constraint optimization for machine learning here at Mila. There's this group at the right who do this at UPenn. And so we were like, oh, we do machine learning with constraints. These guys were like, oh, we do this as well. And usually how constraint optimization problems in machine learning look is like this. You have a loss, you're optimizing ERM, the average loss, you're minimizing that. That's what drives learning. That's what telling your model to learn. And then the constraints say, well, I want that model to abide by something. Fairness, safety, robustness, something like this. We were like, what if we just use constraints and we learn through constraints? So we had a hammer in techniques to solve constraint optimization problems, and we found a nail. You tell me if it's an interesting combination. Okay, so closing parentheses, this is how we solve the problems. There's the Lagrangian formulation, where we're going to transform the constraint problem into an effectively unconstrained one through its Lagrangian. So we're going to introduce some variables called the Lagrange multipliers. These are non-negative scalars, one per constraint. We're going to compute this quantity called the Lagrangian, which is a linear combination of the losses for each example, weighted by those multipliers. And then it turns out that finding a min-max point of this Lagrangian, where we minimize over the choice of model and we maximize over the multipliers, is equivalent to solving the original problem. It's actually easy to see. So if you fix a theta, and then you maximize over lambda, this is what you get. Can somebody tell me why that's the case? Exactly. So it's you're solving a linear problem with respect to lambda. If the thing next to lambda, the coefficient is positive, the best thing lambda can do is go to infinity. It's an unbounded linear problem. So, and what does it mean for this to be positive? It means you're not satisfying the constraint G is over epsilon. And then on the other side of things, if this is 0 or negative, then, since lambda is bounded from below, it cannot go to negative infinity, it must stay at 0, and that's the maximum value. So this thing on the left is like a soft version of the problem on the right. And the problem on the right is just the problem we want to solve. It's the feasible learning problem in different words. I won't go into the details of like constraint optimization and this sort of stuff, but for now, let's just assume there's strong duality for this problem and we can swap the min and the max. And we'll assume this is the case and we'll try to find a saddle point of the Lagrangian. And we do this by minimizing, so we take descent steps with respect to the model and we take ascent steps with respect to the multipliers. When you write those out, they look like this. So on the top, the minimization with respect to the model ends up being a weighted ERM, where the weights are given by the multipliers. And then how do we choose those multipliers? Well, they come from this accumulation of the constraint violations. So on every step, you measure how much you're violating the constraint, and you add that to the multiplier. So if you are over the constraint, it's going to increase. The multiplier is going to increase. If you're satisfying it, it's going to decrease. And then we have a projection here to ensure there's no negative multipliers. So intuitively, what's happening here is if you don't classify, if your loss is too high on a point, you increase its multiplier. And that means that point is going to be more important when you compute the primal update. You're going to tell the model to focus more on the gradient of that point than the other ones. And this approach, I'm showing it with gradient descent for simplicity, but you can do whatever you want in both of the updates. You can use Adam for the primal update and so on. This is a quick illustration of the dynamics, how this works. So suppose you have a problem with just one data point. So on the top, I'm plotting the loss for that sample, which we want to be below the dotted line. And on the bottom, we're plotting the multiplier. So there's a few regimes in training. The first one is, well, you're not satisfying the constraint, so the corresponding multiplier should increase. That's what we see here in the first part. And as the multiplier increases, the loss for that point starts to go down. And at a certain point, it passes the critical threshold. And when that happens, now G is smaller than epsilon, and the multiplier can start to decrease. During this phase, there's still a non-zero multiplier. So there's still a notion of, you're still applying pressure to that point, you're still using this gradient. But in a sense, you didn't really have to. And then you get to a point where that point is, you have the loss that you wanted for that point, and the multiplier has decreased enough that it's 0. And now you're not using that point for training. And so what are some nice properties of these updates? It's two things. One is that they're scalable and they're cheap. So essentially, we were doing weighted ERM. That's as expensive as doing ERM, up to the cost of keeping track of the weights. And in particular, updating the dual multipliers is fairly cheap in the sense that you only need to use the value of the losses when computing those updates. There are no backwards to a model involved. So at least you still have to keep track of those multipliers, which is 1 per data point. So that's significant in some applications. But if your model has billions of parameters, it's not too much. And something else about the updates is that they're interpretable in the sense that you're doing weighted ERM. I just explained how these weights change throughout training. So, it's not a big leap from ERM. So any questions with regards to how we solve feasible learning problems? Yes?
Like GA, you can have instability in general, but is this not a problem in your experiment?
Can you define instability?
Well, like even if you go back to the slide, like even if the G is convex, the data, it's not guaranteed to make that.
Yeah, that's true.
So it was just not an issue in the problem you were trying, or did you have to do some other optimizers to get around it?
So it was not an issue in the problems we were trying, and had it been an issue, you can do different things. So doing dual optimism only, like if you replace this with optimistic updates, then it would converge. Even if you don't do optimism on the primal, for example. Sorry?
But it's not an issue.
In the experiments, it was not an issue, but it could be an issue. And in this case, there's also since we're dealing with constraints, there's also the idea of using the augmented Lagrangian method. That also makes a convex problem, like the bilinear setting. If you see it as a constraint optimization problem and you solve it with the augmented Lagrangian, it converges. So you add an extra term with the squared loss, and that becomes quadratic. That makes your function convex around the solution. Yes, strongly convex.
Yeah, strong convexity it'll work.
Exactly. Yeah. Yes.
In the case when the point will only see that you just the full control. I mean, I learned data. How do you work anything?
The updates.
Yeah.
So you get some data, you get a batch, and then what we do in the paper is we compute the loss of that batch. Then we compute a dual update. So you use the evaluated loss to update the multipliers. Then you compute a backward to the model to compute the gradients of the loss. And you compute this update for that subset of the data. So in terms of the data, you're doing stochastic updates. In terms of the multipliers, you're doing coordinate weight updates. And these are aligned. So it's interesting.
So there are 2 questions online. So Juan is asking, can you please describe why those strong or weak directive forwards, or why are you basically swapping the mean and the max?
Yes, so sure. So this problem always satisfies strong duality. And the reason for it is the fact that it doesn't have an objective. So suppose you have a feasible solution to your problem, then this min max the solution is gonna be 0. It's gonna be the value on top.
I think it's really unity because it's infinity on one side and on the other.
Doesn't GF data need to be convex or strong duality?
So if you have a convex problem, well, no, it can be the case in non-convex optimization, but
it can be, but in general, I think it's non-convex at all. So I don't know why you would have strong duality.
not necessarily, indeed.
You don't even have a setup.
True. Yeah. So, well, but because there's a few things. There's the existence of the.
So if you assume there exists one set of points in the non-convex problem, I think it's satisfied with duality.
Weak duality always.
It's equivalent, I think. If you have a saddle point, it's equivalent to strong duality.
Okay.
You can show, yeah, you show min maximum, maximum if there's like if and only if there exists a saddle point.
Yes, yeah, indeed. And that happens at the saddle point, yeah.
Well, for short, because your objective is just zero and it's a feasibility problem. If there is a saddle point in your max min, then basically the objective will be always zero.
Yes, and in fact, the saddle point would be the feasible point, and you can choose the multipliers to be 0. And that gives you a saddle point. Because if you choose the multipliers to be 0, L is just 0. And you get that you get the strong duality. Are you satisfied with that answer? Okay.
Yeah, be satisfied. And second, there is somebody who's asking, is lambda the same for all samples?
No, it's a different one for every sample. Where is my cursor? Okay. It's 1 per sample, but there's the idea. I'm gonna go arrive at. It's a vector, yeah. But you could think of doing some sharing of the multipliers to save some space. Also because there's redundancy a bit in the data points. There's data points that are similar to each other. So you could try to either share these lambdas or like learn an implicit representation for them. But here we just do a vector, yes.
That's it for the online question.
Thank you. So moving on.
Sorry, there was a follow-up. So Maddie is asking again, wouldn't be a problem when the number of samples is too large?
Yeah, computationally it could be a problem, yes.
And yeah, so that means that there will be a problem, but you probably have some samples on the same lambda.
Yes, we didn't try this, but that's a potential future direction. Yeah. It's a good question. So usually what people do is they would start lambda at 0. Because that way you're not assuming you're incorrectly, you're not assuming you're failing to satisfy the constraints. Like you just wait and see whether that's the case. So for example, if you start with a feasible model and you have lambda equals 0, nothing moves, and that makes sense. Is it sensible? Yeah, probably. Well, this is going to be applied in the non-convex setting, so definitely. Any more questions?
To follow up your question, you can estimate the initial value of lambda just by testing every samples and compute the trend derivative of the Lagrangian, and this can be the initial value of lambda. It seems to converge relatively, so I don't think this is necessary.
You said you can initialize lambda as the Lagrangian.
How the derivative of the Lagrangian. And therefore, there are ways to guess what would be the initial value of lambda. But there are like 2 problems. So first, we need to do a pass to do nothing, just initialization, and also the networks tend to move a lot faster at the beginning. So your initial value of lambda might not even be relevant at the first network, because the network parameters are new.
That's very true. And that's why, so when Theo asked the question about how does this look in practice, how does the algorithm look in practice, that's why we update the dual variables first, because you get the loss, which is up to date. That's the model you're going to change. You get its loss, and you first update the multiplier, so you have a recent multiplier once you go and do the primal update. Like it has some recent information. Okay, so now let's talk about what happens if your problem has some outliers or some noisy data. So, the feasible learning problem is ill-posed in this scenario because it could be that it doesn't have a feasible solution regardless of your choice of epsilon. And even if there is a solution, well, if your epsilon is too tight, you might be asking to overfit that noise. This is the way we solve the problem also doesn't help because as we were discussing earlier, the optimal lambda for any invisible point is going to be infinity, and this can lead to numerical issues. In practice, this would look like you try to solve the problem, then lambda keeps on increasing forever, but you still don't classify the point correctly. And so what we do is, okay, we're going to let the model to incorrectly classify some points, but we're going to yeah, I read about it this morning. Nice. This time they didn't kidnap a kid or something like that. So it's usually some hardcore stuff.
Maybe.
So okay, so what was I saying? So we add some slack variables to the constraints, which we denote by U, and we penalize them. So the idea is, okay, there's you can fail to satisfy the constraint in some examples, but not by too much. So this problem has a few nice properties. One of them is that it's always feasible. You can always just choose U to be big enough so that your constraints become vacuous and you satisfy them. Second point is that if the original feasible learning problem has a feasible solution, then you can then that solves this problem as well. And it solves it with the slack set to 0. And you could also go to this scenario if you're in an application where it's a bit unclear how to set the epsilon, or let's say the stuff Ryan was saying, where you might want to be a bit flexible on some examples. There are some design choices here, which I'm going to explain. One of them is, why do we keep epsilon? If we can just optimize for the upper bound U, why not just like get rid of the epsilon and learn the epsilon through U? And the reason is that it keeps the idea that you don't necessarily want to overfit the data points. You could still have a decently big epsilon and have this resilient formulation. Another thing is, why do we choose the L2 norm to penalize the slacks? This is completely a design choice. In fact, we have some ideas about how to try different norms, which would have interesting properties. This choice is nice in the next slide. So it has some nice mathematical properties. And why do you add this alpha? Since you're just scaling the objective, that's irrelevant for the location of the solution. Again, it's true, it doesn't change the location of the solution, but it's going to show up in the algorithm in a second. So this is a problem, and there are a few different ways you could solve this through like different equivalent formulations to this one. The first one is, we do the same thing we did in feasible learning. We have this problem where the primal variables are now theta and U, and you can formulate its Lagrangian, which looks like this. So you could keep U and optimize it as well. Now you can actually solve for U exactly here. And the logic is that you have a quadratic with respect to U. And so that means that for a fixed theta, mean U max lambda becomes a strongly convex concave problem. And you can find the exact solution for U star, which turns out to be lambda. And so if you replace that in the Lagrangian, you get to this new Lagrangian, which is the same thing as the Lagrangian for feasible learning, but now you have some, you can see it as dual regularization. And then, now you have a quadratic on lambda, so you could also solve for lambda exactly. And if you do that, you get here a problem where you get the loss, you clamp it at epsilon. Like if it's below epsilon, you don't do anything. If it's above, you get it and you square it, and then you minimize that. These are all equivalent formulations in terms of the theta solution.
If we're using strong duality place, bring them in inside, remove the U, turn the outside.
So you are using strong duality here, yes.
You need that whole principle.
But we don't need it to hold for theta. So the point is you fix theta, and then mean over u max over lambda is strongly dual. Like this problem for a fixed theta has a saddle point in u and lambda. And we prove that in the paper. It's because it's a quadratic on u and it's linear on lambda. Why is it some of us but not everyone?
So then you're assuming that minimizing, like min of theta, like that thing is equivalent to min of theta over min max of u.
It is that.
Yeah, you can split the mean into it's element and the notion.
And you can also get down here, like by directly solving from u on top. Because if you solve for u on top, you get u equals this. So you already get the objective. And then the constraints become vacuous. They become g less than or equal to g ReLU of g. So you can also, go directly from here to there. Okay, so this is the formulation we choose, the one that looks a lot like a Lagrangian. The reason we do that is, well, so that we don't have to keep track of the slacks explicitly, which might need a different optimization setup. And, there's also like this problem on the bottom, but the fact that you square the losses leads to a lot of numerical issues. You get vanishing gradients because when your gradient is small, it becomes even smaller, and you get exploding gradients. So this is the formulation we stick to, and we do gradient descent on it, the same as we would do for feasible learning. Here it's nice because now you have strong concavity on lambda, which also helps with convergence. Any questions? Yes?
So we do the combination margin and because it seems that basically when I'm throwing the step, basically we end up with something very similar, but with so let's say you use the two norms, no, you will end up with the dual of the.
That's my guess, yeah. But I actually haven't done the math, but that's my guess.
That's the case because basically you max over lambda, basically the solution of this is the dual of the. That was the definition of the. So,
okay.
And I was wondering why using the L2 norm instead of the L1 norm, for instance. So the L1 norm makes more sense.
Sure.
Because if you have like specific samples that cannot be learned, then you will just discard some of this sample because the L1 norm will incentivize you to be sparse.
I agree with you. In fact, I would go a step further and say the LCO norm would make even more sense. And we may or may not be working on experiments with this at this very moment.
Yeah, so yeah, if you replace it by the L1 norm not even square, you will end up with the infinite enough for that.
Sure. Yeah. Right?
So wait, why not just use this attempt enough? Why?
The one in the bottom?
Yeah, why are you going back to why are you going to the one above? Why not just use the scalar?
So we actually used both in the paper. The last one was very hard to tune.
What was
like the learning rate?
the learning? No, isn't it related to like Cooper loss and like clipping errors and stuff like this?
There is clipping, and I think that's fine. I think it's the squaring that was an issue for us.
But you can unsquare it.
True, yeah.
Because it's the square and non-square share the same minima. So
True, yeah. So there's also a notion of the optimization that dynamics when you have these multipliers are interesting. So, I mean, I know that's a bit of a weak statement because I'm not claiming they are better in any way, but they are different. And in particular, they are richer than the ERM dynamics because they're a generalization of the ERM dynamics. So that there's at least a curiosity question of, well, where do those get you? could also see this as a bit of the hammer and the nail issue. Like we are used to doing this, so we just did that here. That's a valid interpretation as well. Yeah.
Could you interpret the last one as DRM with some other choice of stats, just more purposely? So,
Yeah.
and I get satisfied as soon as they're close. Like
Yes.
central.
Indeed. I guess it might also be connected to like label smoothing. But yeah,
Have you tried with an L1?
we didn't know. It's a good point.
But yeah, I think we can put in kind of loss on make it a way to see how.
Yes.
Yeah, sorry, just a question on reach. The G theta is the loss on the whole.
It's a vector of losses.
So like in the last objective, I guess if you're like you can interpret it as kind of like an expectation within this very norm. If you take an expectation
Yes.
of the data set. So I guess like if you're thinking of like sample complexity in DRM thing, you could use similar techniques to analyze the sample complexity that people learn.
Yes.
Right? Could you with the min-max?
I mean, probably, but I'm not sure. Like, this is part of like the future work, things I'm interested in, sort of stuff. Like that, also like, what's the implicit bias of this method? Like when you solve it via this approach, let's say, do you also recover the max margin solution for linearly separable data? Do you get somewhere else? Like, there's a few questions of like understanding what the fuck is this doing in the end. Like, sorry, we're gonna get canceled for the. Any more questions? Yeah.
I think it's very natural. Because L2 is very much very very specific on outliers, like a quick on outliers. So just choosing where the outliers are. It's a very natural interpretation. Like anything that's G theta that's above epsilon is it will be in this like is not gonna have a grade it's gonna have non-zero gradient. And then L2 already is like naturally outliers. So it's quite natural.
Makes sense. The only issue is the sparsity aspect. Like it'd be nice if you could have a sparse lax, so you only violate a certain number of constraints. Whereas for you could end up violating all of them for the L2 norm.
But then it's this question of like how do you pick the points? Like you really want like from a fairness now, it's like you want to spread the slack all across all the data,
Yeah.
or do you really want like have it sparse, kind of on real based on population?
I agree. Yeah.
You just ignore the an advantage I see with the last one also is that if you want to go like fully online, where like you never see twice the same data points, like I could see it with the last one, but yes, if you wanted to do that,
that's right. So in fact, if you do that with the Lagrangian formulation, updating the dual variables first, you end up doing this same thing in practice. Because so the first loss, if you initialize lambda at 0, the first loss is this G minus epsilon. And then you would multiply that. So G minus epsilon, and you project because of the lambda update during the projection. So that would be the coefficient of G for ERM. So it's this, essentially.
Yeah, I'm trying that. So you're saying like you have an infinite many go back to the
So suppose you update lambda first, doing the same step. So lambda 1 is going to be 0 plus G minus epsilon, and then you have a projection. So G minus epsilon projected. And when you plug that here for the primal update, so you have G minus epsilon projected times the gradient of G is your update.
Gradient.
Exactly. Yeah. Okay, any more questions? So this is what we solve in the resilient case. Now experiments, shameless plug. So for the experiments, we use Cooper, which is this very amazing library for constraint optimization and machine learning. You just need your quantities to be differentiable. So if you're curious, check it out.
There's no conflict in this case.
No. So, okay, so I have a few experiments. I might go a bit quickly, so tell me if you want to stop because I want to get to the future work.
We have 20 minutes left. Right, we have the room until 20 minutes.
Okay,
And like 5 minutes. That's it.
sounds good. Thanks. So this is just a visualization of what happens when you solve a problem with feasible learning. So here we're using a neural network to classify this 2 moons data set. I believe we were asking for 60% confidence in the predictions. And you know, the size of each of these points corresponds to the value of the Lagrange multiplier when we stop training. So you can see that points closer to the boundary have larger multipliers, which makes sense. Those are the points that define, in a sense, the boundary. Those are the harder points. So throughout training, they were the ones that were not satisfying the constraints for a long amount of time. And it looks a bit like a soft version of an SVM, where you don't have like some support vectors, but you have a bunch of support vectors, but all of them contributing a little bit to the overall balance of the decision boundary. We tried it like in ERMs on turf, like how does this perform in terms of average performance? Essentially it performs similarly well to ERM. It's worse. You know, it's not trying to optimize for average performance, so it makes sense that it would be worse, but it's also not catastrophic, like it works. There's also, and this is one of the interesting results in the paper. Here we were doing some preference optimization in language models, and we're plotting the loss, so a CDF of the loss. So to the right, you have samples with higher losses, and to the left, samples with smaller losses. You can see that these two CDFs have different shapes. So for ERM, you know, you have a bunch of samples with very small loss, but then you also have a series of examples with a huge loss. Feasible learning compacts this a bit, so the average is not as good, but the tail is a lot smaller, and this carries over to the test set as well. So, you know, this is like showing the fairness aspect of feasible learning, essentially. And there's a bit the notion of overfitting. We didn't explore this as much, so I'm not gonna say feasible learning overfits less, but we had this toy example where we had a polynomial regression. So here we actually have 20 points we wanna fit, and we have polynomials of different degrees, 10, 20, and 30. When we solve them with FL and ERM, for feasible learning, we don't ask for 0 squared error. We have some margin. And then you can see that the solutions of feasible learning are a lot more smooth. So again, earlier I mentioned you could also get to the ERM solutions, like the red curves are also valid solutions to the FL problem here, but for some reason we get to smoother ones in practice. So this could be something of an indicator towards what's the implicit bias of feasible learning via the primal-dual approach.
Do you think this could be the change when labels are very nice? Or in this case, there's no really noise in the labels?
So for this specific experiment,
Yeah.
there is some noise. So I think we use a sine curve and we add a bit of noise.
Do you think that for a lot of noise, it could be the opposite?
Good question, maybe.
I'm sad about
Right, but then you could use resilient feasible learning. That would potentially help. Well, in a sense, all of these experiments have early stopping, because in none of these we train. Let's say for feasible learning, we don't train until all the multipliers are 0, and for ERM, well, there's no for the cross entropy loss. You're always doing early stopping in a sense.
Actually, I think in your case, it's kind of a soft uncertainty because you stop learning on some example once they reach
That's true.
epsilon, and the one that doesn't have one still learn on them.
That's true.
And then it's not like everything's been less.
That's true.
To do that on the validation, that's also.
To keep track of the multipliers. Okay. So I'm going to skip this, but the point is it's not more difficult to tune than ERM. Okay. So that's essentially the main part of the presentation. Now I have a bunch of like future work where I would like everyone to give their opinions. If you have come up with some interesting direction now that I've been talking about feasible learning for a while, let me know. Feel free to step in. We can make this a bit of a blend between the last couple of slides and the discussion at the end. So there's different axes along which I think feasible learning could be interesting. One is like applying it on places where the sample-centric nature could be useful. We also have ideas on how to enhance feasible learning, stuff about the norm you use for resilience, for example, or like trying different dual updates that might be faster and so on. And there's questions about understanding, why does it overfit? Does it not overfit? Why? So there's a connection between feasible learning and exact learning, which is the idea that you want to fit. You don't want to learn statistical patterns. You want to memorize your data. This is useful in settings. Well, not memorize, but you want to like learn stuff exactly. And this is useful in applications such as reasoning, or like, when you want your model to follow a series of specific steps, as opposed to taking a statistical shortcut. There is some recent work from DeepMind people arguing that if we want to get to general intelligence, we need to focus a bit more on exact learning and a bit less on statistical learning, because statistical learning is very slow and very sample inefficient. So, the reason I bring these things up is that feasible learning, at least in a sense, it feels like a step in the direction towards more exact learning, where you can say, I want to be perfectly good, at least on some samples. And so that's one application that could benefit from feasible learning. There's also the idea of heavy, if you have heavy tail problems, where, usually you would either rebalance the data or reweight the data. Well, feasible learning is doing this for you through the Lagrange multipliers. And you could also like design a different problem where, let's say you have some data that is very important. You want to make sure your model does well on that data. But then there's a bunch of, let's say, not so great noisy data that you still want to have in the training loop, but it's not as important. So one idea here is you could constrain the loss on the important data to be very small, and then you just minimize the average over the rest of the data. So that here there's a clear hierarchy between which data points are more important to you and which are not. One could also exploit the informativity that the multipliers bring, because these tell you like, these point you towards hard samples, easy samples, so they could be used to flag potential outliers in a data set. There's this notion about like when you have a 0 multiplier, you're not even using that data point for training. So you could you could design some system where if a point has had a zero multiplier for a while, you just discard it. And now training, you're kind of speeding up training, whereas ERM would look at it all the time. Okay. There's also stuff on like what we could do with feasible learning to improve it. I had here like the oceanomus slacks if you want to make sure your slacks are sparse. We also consider very basic ways of updating the multipliers, just gradient ascent. But you could have something different. You could have like exponential updates that might be faster. There's also the notion that once you classify a point correctly, the multiplier is not zero immediately. It takes a while to go back down to zero, so you're still penalizing that point. And so you're still overfitting that point for a while. So you could think of updates that downweight this multiplier even faster. There's the stuff we mentioned about, maybe having shared multipliers or an implicit representation to save some space. This also builds on the fact that samples can be very redundant. And this also helps in the online setting. Like if you have a model that gives you the correct multiplier, you just put your new data point in the model. There's stuff on understanding feasible learning. Is it better in terms of overfitting, calibration? What's its implicit bias? Does it get you to better solutions and this sort of stuff? And that's it. Yes.
Thanks for the nice presentation.
Yes.
I'm really interested in the generalization aspect and especially some like components to ERM. Can you go back to the polynomial figure? This one. So you have like this double descent phenomenon, right? Like if you keep increasing the degree of the polynomial, like at some point, you have enough capacity to interpolate. But if you keep going, and if you keep increasing the degree of the polynomial, and if you sort of have some regularization that makes your coefficient small, can be implicit or explicit. I'm not sure if this works with any polynomial, like for some basis this works. You're gonna find solutions that are very smooth.
Sure.
And I think my understanding of this is that as you increase the capacity of the model, you have more at some point you have more interpolating solutions. The space of solution for ERM becomes bigger.
Makes sense.
And if you have a regularization for smoothness, like in some maybe like implicit or not, you're gonna favor interpolating solutions that are smooth. And as you increase the capacity of the model, you'll have more choice for such solutions. So that's why that's one explanation for why these things are happening. But what's interesting here is that to have like a similar thing happening with this feasible learning scenario, because of the sort of the epsilon in your loss, it seems like you also like, for instance, with degree 10 or let's say degree 20, you already have like a very large set of solutions because of this epsilon. Right? Whereas for ERM, let's say, I don't know if this is the case here, but let's say you have only one solution. Because I think the epsilon key that so that's the case here, only one solution. But for feasible learning, you have a bunch of solutions.
Yes.
And somehow maybe also in your algorithm, you have some kind of implicit bias that favors smoother solutions. And I think this could be like pretty interesting because you could get like good generalization or like a smooth bias without having like super large number of hyperparameters, a large number of parameters. Like you have good generalization without hyperparameterization.
Right.
So I think that would be interesting.
I agree. Interesting stuff. Especially since there's no objective. Like we could have added that, let's say, minimize the norm of the model, which that also maybe pushes you a bit towards better generalizing solutions, but that's not the case here. So
Yeah, yeah.
it's interesting.
I'm just.
We didn't, I think. Yes, exactly.
But we know there's like some implicit visualization already in your right?
Yeah.
With
SGD.
Actually, there's implicit visualization. So the loss has nothing to do with implicit visualization. Because as long as you're looking for a solution, well, I mean, any algorithm that minimize the error will conduct a minimum of the error. And if there are multiple solutions of this, then this is the algorithm that chooses of its bias towards the solution. Essentially, is minimal solution. The other that probably something like the center. Not in
Yes.
this way, that's the parameterization. Yeah, on the parameterization also influences that. So that could be nice to be like speak it as picture without computing.
Indeed. And as just to say something I said earlier again, here the dynamics of the primal-dual algorithm, they're a generalization of the ERM dynamics. Like if you were to initialize the multipliers to 1 and not update the multipliers, you get ERM. So there's, that means that you can at least you can potentially get the same benefits from ERM and then perhaps something more interesting. Yes?
Have you thought about it for looking into like the link between deep learning and like risk sensitive optimization and like world-class optimization? Like the I guess if people learning kind of reminds me of this like additional value of risk instead of optimizing like expectation around variable, you optimize like at least under some assumptions of expectation given that the sample is like below some quantile, like basically additional expectation in the like negative tail of the variable. Which looks kind of like when you near the except you have like a different quantile HS or sample. I don't know if it's exactly the same thing.
So yeah, I haven't looked at that, but I definitely will.
Okay. Yeah, good thought.
Thank you. There's also a notion of what's the correct way to look at physical learning in terms of generalization, because it's not optimizing for average performance. So why would you look at an average loss bound? I mean, it might be better in practice because of this like non-zero epsilon stuff, but I think that there might be a different way to look at generalization in physical learning. It could be like what's the probability that you get a sample and it satisfies the constraint, something like this. And that might be connected to what you were saying.
It sounds like yeah.
Okay.
I don't know if they're exactly the same. It sounds like
Right.
maybe.
Food for thought. Thanks. Do we have questions online?
Oh, yes. What is your current view on what's the high conversion of generalization should be for as opposed to the one something
Yeah, it could be either what's the probability that you get a new sample and it satisfies the loss, or yeah, maybe something like that. I'm not sure. I haven't thought much about this, to be honest. Can you say that again? Oh. So you're saying the upper bound epsilon. So we only use the same for everything. How do you consider? So, I guess in some specific applications, one might be interested in like tweaking this, but it's also like too many parameters. So I think if you're really like into tweaking this, you might do it like for groups. Like for this group, I have to perform really well because these are my important customers, so small epsilon. For this group, I don't really care, like something like this. Yep.
What's it?
So for classification, it's more clear, let's say, for classification than for regression, because it at least needs to say classify the point correctly. Now it's very application dependent, which is also why it's important to have the resilient formulation. So if you don't know, well, at least add the slacks so that you have some flexibility. Thanks. Thank you. Any more questions? Thank you.
I want to